All right, in this example, you have a cooked problem. It's made up with marmots and populations. And the expectation here is that you're going to go to your book and look at the nonlinear discrete dynamical systems section and the logistic model, which they talk about. So if you go to your book, which I have right here, and you search under logistic model, you end up going to page 110 and you see the logistic model right here with the same letters that they have in the problem, which R and C are being used. So if you go back to your problem, you'll see that R in this case is 0.7 and C is 810. There's a lot to this. There's a lot underlying this. What we're doing here is we're using something it's called the Verhulst model. He was a biologist and he was studying populations. And what he said is that, hey, populations don't just grow without bound. What's going to happen is when you're far away from a carrying capacity, you're going to be able to grow great because resources are going to be there, life is going to be great. But the closer you get to that carrying capacity, life gets harsher, and people will not have as many babies. It's harder to survive. Or as you hit that carrying capacity, your population is going to plateau. And so that's the idea behind the Verhulst model, the bigger picture. I do want to tell you more. These one-dimensional models are complicated. They're very cool. There's a whole area of math just devoted to studying models like this. And I was trained in that. I'm what we call a dynamicist. So I feel like Imhotep on The Mummy. I just want to yell and tell you everything. But I'm going to hold myself back. We're going to go through this cooked problem and just punch in numbers. So here we go. This is from your book, page 110. That's the formula. You identify the C and the R. There they are. Plug them in. I also know that P0 is 300. So plug in. And then this model, the way it's set up, the way that the book is thinking of it, is they're thinking of it as a difference equation. So they have Pn minus 1 here. So you have to solve for Pn. So bring the Pn minus 1 over. And consider this new model here in this way. And then to answer the first question, iterate it on Excel. So like Rachel Ray, I already have it half cooked here. That's not really the way that if you watch Brian Regan, who's my favorite comedian, he'll talk about how it's actually difficult to do this from scratch. Let me tell you how to do this from scratch. So it's just like setting up a normal one-dimensional linear DDS. You put your 0 here, you put in here this is my years, and this is what it means. All those things you can put in. Instead of A, you're going to have, this is actually the wrong model, but let me go to our model right here. So instead of A here, you have R. And instead of C here, you have instead of D here, you have a C. And you put in the numbers for those two values. In our model, the R was 0.7 and the C was 810. And then initial condition was at 2015, it's 300. And then I do the same thing as I did before. I do A2 plus 1 to get the next year. And over here, I'm going to have something a little bit different. Wherever I have Pn minus 1 here, I'm going to replace it with B2 because B2 is my previous step. And wherever I have the R, I'm going to put $2 because that's where R lives. And wherever I have C, the 810, I'm going to replace it with $2 because that's exactly where I have the value of C housed. And then I hit enter and I scroll these both down, go to the cross and I scroll them down. It's already been done. And you can see in 2016, there are 432. I rounded down because there's no such thing as 432.2 marmots. And in 2020, I have 794 marmots. I rounded it up because I don't have 790. There's no such thing as a half a marmot. And so that's what goes into these two blanks. The next thing you're asked for is the equilibrium values of the system. I'm going to show you how to get them from scratch, although the formula for the Verhulst model or the logistic model is in your book. So the next step to find the equilibrium value is you first let Pn minus 1 and Pn be equal to each other and P bar. So you replace anything in this equation that has a n, sub n in it, you replace it with P bar. So that's what I did here. And then you solve this equation. And I didn't know what to expect if they were clean. I don't want to factor this thing. So I went to Wolfram Alpha and I put in that that formula that I just have, and I told it to solve. So you can do the same. If you haven't used Wolfram Alpha before, we're about to use Mathematica very soon. And it gave me in the solution x equals 0 and x equals 810. So those are my two equilibrium values, 0 and 810. This is also different than what you had before because we used to have only one equilibrium or no equilibrium values. Now we can have two. And so that's how you do this problem. You put into the last slot 0, 810. By the way, the formula for the logistic model's equilibrium values are in your book. It turns out one is the carrying capacity and one is extinction, 0. But I wanted to show you how to do that from scratch because the next problem we'll have to do it again.